Let us answer the problems from this book, Strength of Materials, 4th edition by Pytel and Singer. Let's start with chapter 1. Chapter 1 is simple stress. Let's go to page 12. Let's try and answer problems 104 and 105 for this video. Let's start with problem 104. A hollow steel tube with an inside diameter of 100 millimeters must carry a tensile load of 400 kilonewtons. Determine the outside diameter of the tube if the stress is limited to 120 megapascals or meganewton per square meter. Okay, so let me use MathCAD to solve this one. We're given the inside diameter. Let's call that D subscript I equals 100 millimeters. So instead of putting a unit here like this one, I'm just going to write this unit outside D here, because MathCAD will automatically convert units, and I want to show you also in my solutions how are we going to convert units to get the correct answer. The tensile load is also given. Let's call it T equals 400 kilonewtons. And what else? We're given the tensile stress. Let's call it sigma equals 120 meganewton per square meter or megapascal. So we are asked for the outside diameter. So our stress is equal to force over area. In this case, our force is the tensile force T divided by the area. That area is the cross-sectional area of the hollow tube. Okay, so we have a hollow steel tube. Okay, so we have the cross-section of the hollow steel tube. This is the inside diameter, which is given to be 200 millimeters, and this is what is asked the outside diameter. So the area we're talking about is this shaded portion. So it will just be the area of this outer circle minus this inner circle. So that's equal to the area of the outer circle is pi times d sub o square over 4 minus pi times d sub I square over 4. Or this is equal to pi over 4 times this minus this. So this equation becomes, I'll substitute A with this, and then the equation becomes like this. Okay, so let's check the units. The left side of the equation is in megapascal. That's meganewton per square meter, or megapascal is also the same as newton per square millimeters. This is the same as meganewton per square meter or megapascal. Okay, so take note of this. So again, the left side of the equation is newton per square millimeter. And the right side of the equation, T is given as 400 kilonewtons, while the diameters in the denominator, D sub I is in millimeters. So we will convert these kilonewtons to newton so that I will have newton per square milli on the right and newton per square millimeter also on the left. So to do that, I'll multiply this by 1000. So this is now newtons. So let's solve for D sub O. So what I'm going to do now, first I'm going to move this 4 upwards to the numerator. Let's multiply this by 4 and then multiply the whole equation by this quantity so that will cancel out here on the right side of the equation and will be multiplied here on the left side of the equation. Next, I'm going to divide the whole equation by sigma. So this divided by sigma will be 1. This divided by sigma will be like this. Then I'm going to remove the parentheses here and transpose the second term to the right side, and it will become positive here on the right side. And finally, I'm going to find the square root of this equation so that the left side of the equation becomes D sub O, while this side of the equation becomes the square root of that. So therefore, D sub O equals 119.35 millimeters. So this is problem 104 on page 12. Okay. Next, problem 105. A homogeneous 800 kilogram bar AB is supported at either end by a cable as shown in figure 3-105. Calculate the smallest area of each cable if the stress is not to exceed 90 megapascal in bronze and 120 megapascal in steel. Okay, so what are given here? We have the mass of the bar equals 800 kilograms. What else? The stresses in each material. We have stress for steel. We have stress for bronze equals 90 megapascal. And the stress for steel is 120 megapascal. So first we'll draw the free body diagram of bar AB. So we are going to cut these cables here. Let's cut the cable. This, since we cut the cable, it will be replaced by tensile forces going in this direction. So this will be a tensile force for the bronze. And this is the internal tensile force for the steel. And then we also have of course, the weight of the homogeneous bar. If you look at the free body diagram, you can see clearly that each of the cable will carry the same load because of symmetry. That means T sub BR is equal to T sub ST equal to W over 2. And W is the mass times 9.81, and this is equal to 7848 newtons. So that means this equals W over 2 is 3942 newtons. And this is the same value for steel. So with T sub BR and T sub ST known, and we have the allowable stresses 90 for bronze and 120 megapascal for steel, we can now solve the area in each of the material because stress is equal to force divided by area. That means area is force divided by the stress. So for the bronze, area subscript BR is equal to T subscript BR divided by the stress for the bronze. This is equal to 43.6. So since the force is already in Newton, the stress is in Newton per square millimeter. That means the result is square millimeters. For steel, let's just replace the subscript to ST, and that's the area for the steel. 43.6 for bronze and 32.7 square millimeters for steel.